All right. Thank you, everybody, survivors and everyone who's still here. And we're very grateful to Sheel, who is going to give the last and most exciting talk on Rabinowitz RAP Fukaya categories and the categorical form of neighborhood at infinity.
Okay, thanks very much, Tony, and thanks to the organizers for the invitation to speak here. It's great to see all of you, and thanks for staying through. Yes, the title of my talk is Rabinowitz RAP Fukaya categories in the categorical formal punctured neighborhood of infinity. What I want to do in this talk is introduce this category, the Rabinowitz Fukaya category or wrapped Fukaya category. It's a version of the wrapped Fukaya category, which is a bit different than the usual wrapped Fukaya category, but related certainly. And the second thing I want to tell you about is the relationship to the usual wrapped Fukaya category. And here we follow a proposal or conjecture of Abuside using an algebraic construction of Fmov that is sort of a purely non-commutative construction using that depends only on some DG or A infinity category. What I'm going to say today, everything is based on joint work in progress with Yuan Gao and Sarah Venkatesh. So first, let me tell you what is Rabinowitz Floer homology. So Rabinowitz wrapped Fukaya category is an open string version of this closed string theory that's been around for a bit longer. It was introduced by Chilebach and Frauenfelder in 2007. Originally, it was defined as a semi-infinite Morse homology for an action functional introduced by Rabinowitz, a different action functional from the usual one. I'm not going to focus on that interpretation so much. I'll give you a different definition in a minute. But what you get out of it is an invariant of a, say, contact type hypersurface in a Liouville manifold, for instance. We typically won't focus on this RFH of H and X. We'll just focus on what I'll call RFH of X, which is the case that the hypersurface itself is essentially equivalent to the boundary at infinity of the Liouville manifold. So for instance, if your Liouville manifold is the completion of some Liouville domain, then you could just take H to be the boundary of this Liouville domain right here. Okay, so and the resulting theories, the resulting theory we'll call RFH of X, and that's what will be the focus of the closed string story. And we'll generalize, we'll look at open string version of that. So what goes into this complex? Well, as a chain complex, it's generated by all Rabe orbits on this sort of contact boundary. By this, I mean positive, negative, and constant Rabe orbits. Okay, so normally when we think of Floer theory, maybe we think of something involving positive orbits, so on, but here we use all orbits. We also add in constant orbits, which contribute, you could think of them as contributing by some sort of more spot theory, a cochains of the boundary, to the chain complex. Okay, so now there's a theorem subsequently proved by Chilebach, Frauenfelder, and Onsha, and we'll take this theorem to be the starting point. It'll be our definition following a definition of Sarah Venkatesh. We'll just define this Rabinowitz Floer homology in terms of invariance we've seen before in mirror symmetry. So we'll define the Rabinowitz Floer homology of a Liouville manifold X to be the cohomology of the mapping cone of a canonical map between two terms that I'll recall for you. So the rightmost term is the symplectic cohomology chain complex. Okay, so this is what we think of as the usual open string, the usual closed string invariant of a Liouville manifold that's, say, like, isomorphic to the Hochschild invariance of the wrapped Fukaya category in favorable cases. This is the cohomology of a complex involving, for instance, the cochains of X and Rabe orbits, positive Rabe orbits. Okay, and cochains sit inside as a subcomplex. The left-hand term has been studied too, but maybe a little bit less so in the mirror symmetry literature. This is what's often called the symplectic homology chain complex. So the way you could think of it first is just by looking at negative orbits instead of positive orbits. So we just sort of will look at, the cohomology of a chain complex, involving negative Rabe orbits, and some interior contributions, which will contribute a compactly supported cochains of X. It doesn't contribute cochains anymore. And this compactly supported cochains of X, you should think of as a quotient complex. So you could also think of this map, this second thing, okay, by some sort of Poincare duality. Of course, you could think of it as the linear dual of the symplectic cochain complex. Okay, so there's an isomorphism. Between the symplectic homology chain complex and the symplectic cohomology chain complex, dual shifted by the suitable dimension of your space. This is coming from the usual by Poincare duality and Floer theory. That means, by that I mean, if you look at the Floer homology of negative a Hamiltonian, it sort of gives you the linear dual theory with a dimension shift. Okay, so these are the two pieces. Both of them are sort of essentially, well, at least symplectic homology is formally determined by symplectic cohomology. There's one piece of information that isn't determined by symplectic cohomology, which is this map. So I want to explain this map C. It's a continuation map. Okay. So on the cohomology level, it's given by the natural map that's obtained by first projecting to the quotient complex here from symplectic homology, then mapping compactly supported chains to compactly supported cochains to cochains. There's a canonical map between them, and then cochains is a subcomplex of the symplectic cohomology complex, so it maps to symplectic cohomology. Okay, so there's a canonical map. As you can see, symplectic cohomology we expect to be infinite dimensional, but this map factors through something finite, so it's highly degenerate. Okay, so but it's still often non-zero in examples. Okay, so we could just take this to be the definition of this Rabinowitz Floer homology group for our purposes. And what I want to emphasize before talking about the open string version of the theory is this, in some sense, this theory, Rabinowitz Floer homology, is some sort of boundary invariant in the sense that it detects some sort of non-triviality or the existence of a boundary in favorable circumstances. So here are some pieces of information about this invariant that somewhat support that. So for instance, in the non-exact case, when I have a compact manifold, this Floer homology group is 0 by Poincare duality, right? So in that case, all I have is Floer homology on both sides, and I just have a continuation map. It's an isomorphism. In general, if this Floer homology group is 0, then symplectic cohomology is finite dimensional, even in the non-exact case when it's defined. Okay, so now in the exact Liouville case, there's a sharper result that's true. So Ritter proved that this group vanishes if and only if the ordinary symplectic cohomology vanishes. Now, here's one other hypothetical scenario in which we understand this group. Well, suppose there don't exist non-constant Rabe orbits. Okay, so that's supposed to never happen, but let's suppose there were no non-constant Rabe orbits on our contact manifold. Well, then we still have a constant orbits contributing. And so this Rabinowitz Floer homology group would be just the cohomology of the boundary. Okay, so so here just sort of a few pieces of information about this group. Any questions about this group? So what I'm going to do next is talk about the open string version, where I'll sort of step through all of these pieces a little bit more slowly. So for the open string version of this theory, what I want to do is from the beginning, we're going to use the analog of this definition, which which you could think of as just a theorem or a definition. We'll use that to define our open string Rabinowitz theory, rather than using Morse homology of the Rabinowitz functional, although there is work in that direction also by Mary and Bonia. So how does this go? Well, we'll start with a pair of Lagrangians, K and L, that are properly embedded, exact Lagrangians, not necessarily compact, but they should be cylindrical at infinity, right? So the sort of Lagrangians I have in mind, they could run like this. So if K and L is such a pair of Lagrangians, as usual, in fact, we can define ordinary Floer cohomology. This is the usual HF of a pair of Lagrangians, as long as they're disjoint at infinity. Okay, so this is the usual Floer cohomology generated by intersection points and holomorphic disks. Now, there's some additional structure to this system of groups. So for a positive at infinity isotopy, so if I have an isotopy K0 to K1, that's positive at infinity. Okay, so what does positive at infinity mean? Well, there's a canonical positive direction at infinity, at the boundary of at infinity of any Liouville manifold. Okay, so this is the, here it is. This, you could think of it as the Rabe direction. So for a positive at infinity isotopy from K0 to K1, we get a map from HF of K0L to HF of K1L, the continuation map. Okay, this map is in general not an isomorphism for these sorts of non-compactly supported isotopies. And so wrapped Floer homology is by its definition meant to sort of fix this lack of isotopy invariance. So you can define ordinary wrapped Floer homology, HW of KL, as the direct limit over positive wrappings from K of HF of that wrapping with L. And by a slight elaboration on what I said so far, well, these HFs fit into a direct system, so I can take their direct limit. This is okay, so this is wrapped Floer cohomology. And this is these are the cohomological morphisms of a category we're more familiar with. So these are the cohomology of morphisms in the Rapp-Fukaya category. Okay, but there's also another thing we can do, which is analogous to the symplectic homology construction. So instead of positively wrapping, we can just negatively wrap. And when we negatively wrap, we get an inverse system. Okay, so when we get an inverse system, we can take the inverse limit. So we'll define the HW lower star of KL to be the direct limit over negative wrappings. Sorry, the inverse limit over negative wrappings. Or you could think of them as positive wrappings to K, as opposed to positive wrappings from K of HF of the negatively wrapped version of K with L. Okay, So I'll call this wrapped Floer homology. Or I might call this negatively wrapped Floer theory. Okay. And I want to study the relationship between these two. Well, okay, before I talk about the Rabinowitz Floer homology, so the Rabinowitz Floer homology, again, is going to be the cone of a natural map. Actually, maybe let me define that already. So there's a map. Okay, so there's also a map. Which I'll just call C for continuation. Again, from the negatively wrapped theory. To the positively wrapped Floer homology group. Okay, it factors through ordinary Floer cohomology. So again, it's fairly degenerate because ordinary HF is finite dimensional, whereas these HW upper star and lower star might be infinite dimensional. So there's this map and we'll define Rabinowitz theory to be the cone of it. But let me just say a minute more about this map. So for k equals L, again, the map factors through. So let's just consider the case of HWKK. Well, this map C factors through HF of K wrapped a very small amount by minus epsilon, which maps by continuation to K wrapped a small positive amount, and then tested with K, which then maps to HW upper star. Okay, and the reason I want to mention this is, well, these two for sufficiently small epsilon. This is, again, the compactly supported cohomology of K and the cohomology of K, and this is the canonical map from topology. Okay, so it factors through this canonical, somewhat degenerate map. Okay. And again, we can define the Rabinowitz wrapped Floer homology of KL to be the cohomology of the chain level mapping cone.
Sorry, Sheel, a question.
Yes, sure.
In the KK case,
Yes.
there will be somewhere in between, there will be the Floer homology of KK, just the ordinary Floer homology of KK. Where is it sitting?
Yeah.
Is it sitting between the compactly supported guys and HK?
Right. So, well, there's a question about how to define HF of KK, given that K intersects itself at infinity. Typically, the convention is one just calls this group on the right. You often just call this HF of KK.
But that's the displacement you're taking to make the definition.
Yeah, you have to choose some convention at infinity, and typically if one
but it's not
writes
like
about
half
HF...
epsilon convention or anything like that.
Sorry?
There isn't some half epsilon convention that will be in between the two middle terms.
No. The minute you've wrapped by a sufficiently small epsilon, they're all isomorphic.
They're all isomorphic. Okay.
So the minute you chose a direction to wrap in, as long as it's sufficiently small, you get the same group. That's right. So I'm sort of just basically not fixing that convention for the time being, and just sort of opting not to define HF of KK. But indeed, we could define it this way. Okay, so this is the Rabinowitz wrapped Floer cohomology. And now to understand what sort of structure it has, I want to tell you a little bit about what structure wrapped Floer cohomology has, to remind you. So first of all, so there's, as I mentioned, these are morphism spaces on the cohomology level. So there's composition, right? So composition in wrapped Floer cohomology comes from the fact that, well, I have an ordinary mu2 between regular Floer cohomology and up to some identification, this ordinary mu2 acts on all these Floer groups. Okay, so if I have an element of HF of phi plus m of k with L, where phi is phi is a positive isotopy, okay, and an element of HF of phi plus n of L with n, then, well, what I'll first do is push, we'll apply phi plus n to both of the both k and L in the first copy. Oops. and then just mu2. Okay, so if I have a somewhat wrapped element of a morphism space and a somewhat wrapped element of a morphism space, I can multiply them and get a somewhat more wrapped element of a morphism space. Okay, and so this is what we get for positive wrapped Floer homology. What's happening with wrapped Floer homology? Well, what happens here is that we don't get, so on the chain level, let me call the resulting structure W minus. It is not a category. Okay, so there's sort of no units. There's an issue with units. But it is a bimodule over the usual positively wrapped Fukaya category. Okay, via the same sort of multiplication. Okay, so given something negatively wrapped, I can multiply it by something positively wrapped to get something a little bit less negatively wrapped. And then if that gets me to something positive wrapped, I just truncate by 0. Okay, so that's sort of the idea. Okay, so W minus is not a category. Nevertheless, it turns out that RW of KL, which is this cone, okay, is a category. Okay, so that's the main thing I want to tell you about for the first part of this talk. Let's see. So I think let me try something.
Sure.
Sure. Question?
Sure. Is there a non-unital product structure on the second thing?
Yeah, but it's kind of uninteresting. So there's this continuation map of bimodules from W minus to W, right? And the product structure, the non-unital product structure is equivalent to just like, if I have 2 elements of W minus, I first push one of them to W, the regular W, and then act on W minus. And so you can prove that it's just equivalent to that.
I see.
Yeah, indeed, that's why I'm not emphasizing it. So for instance, so the analogy should be, you should think something like compactly supported cohomology and cohomology. Okay, so maybe I should write that analogy somewhere. Let me do that. One second. Here we go. Working again.
Symplectic homology was a co-algebra, right? Maybe is there anything like a co-category structure here? Or?
Yeah, there's probably there's likely some structures like that, and I think there might be something to say there. We'll use. I mean, we'll use something. We'll use so that some product structure on this cone complex involves some products of W minus, you know, a pair of elements in W minus multiplying to something in W minus, and that's of course punctured to a co-product on W. So yeah, I didn't completely answer your question, but there are some co-structures arising. I guess I should say that also we have Poincare duality again. W minus is isomorphic to W, the dual diagonal bimodule shifted by some dimension. That's important. So it turns out, as I was mentioning, that here's my copy and paste attempt. It turns out that there is an algebra structure on, for instance, the closed string Rabinowitz Floer homology group, and also RW of LL, or more generally composition maps. And these are compatible with maps, the canonical maps from, you know, symplectic homology and from wrapped Floer homology. They're all algebra maps and so on. And furthermore, this can all be lifted, of course, to chain level structures. So that's what I sort of want to focus on, though I won't talk about all the details of the chain level construction, but this can be lifted to the structure of an A-infinity category, and we're going to call it the Rabinowitz wrapped Fukaya category. And that's the topic of today's talk. We'll denote it by RW of X. The construction actually is implicit already in some work of Venkatesh and Paul Seidel, Lefschetz, the Lefschetz 6 paper. If you look there, there's some related constructions in the context of Fukaya categories of Lefschetz fibrations. Okay, so on these sorts of A-infinity structures on cone complexes. Maybe I can say a word about, I don't want to spend too much time on what the algebraic structure is, but maybe I have a little blurb on where the product structure comes from. Okay, and I think it's enlightening to think about. So these product structures, to construct a product on a cone complex, like RW of LL, for instance, we'll just focus on one object for simplicity here. Well, it requires a variation of secondary operations in the spirit of these Goreski-Hingston coproducts. Okay, so that's, in fact, Chilabach and Onsha, were interested particularly in how the Goreski-Hingston coproduct fits with the usual Chas-Sullivan product, and that's sort of one of the contexts for their work is their other joint work with Hingston on this. So a product on this cone complex, you should think of it as, well, this cone complex has a shifted piece, CW lower star shifted by 1, and a non-shifted piece, CW upper star. Okay, what's a product, a degree 0 product on such a complex? Well, it consists of, so I'm gonna talk about the shifted piece as the minus piece because it's negatively wrapped, and I'll talk about the non-shifted piece as the plus component because it's positively wrapped. Okay, so first of all, they're degree 0 maps, plus plus to plus, plus to minus, and plus minus to minus. The first one is just the algebra structure on usual wrapped Floer homology, and the second, the pair of maps are the module structure of wrapped Floer cohomology on wrapped Floer homology. Okay, that's what we talked about so far. Okay, but then there are degree -1 maps. So this is just even to get a homology product. You need these degree -1 homotopies, both here and here. And these degree -1 maps, I'm not going to focus on all of them. They're just where they have to be. The picture I want to draw your attention to is this one. Okay, so basically, you should think that, okay, let's consider operations from minus to minus. So that's this case. Okay, the first thing I can do is take a minus element, continue it to get a plus element, and then act on the other minus element. Okay, or I could do it in the other direction. I could take the other minus element and continue to get a plus element and act on the minus element. Okay, and it turns out these two are homotopic operations, and I need to fix a choice of homotopy between them. So this is why we say secondary operations. This is the sort of Goreski-Hingston type secondary operation that arises. And then finally, there's a degree -2 map, which is a null homotopy of some combination of all these homotopies. Okay, so I don't want to focus on that too much, but this is some source of where this arises. And so one needs a convenient formalism for keeping track of all of these in the A-infinity world, and there is actually already convenient formalisms in the literature. So this sort of Abuzaid-Seidel popsicle method actually is quite convenient for this, as Seidel observed, I think, in the context of his work.
Is this last part also in Paul's work, like in his non-commutative pencils, or
which last part?
The degree -2 map, does it exist in that?
I think in his case it might be 0 for some formal reasons, but in our case it definitely exists.
Okay.
Okay, so we have this complex. It has a category structure, and again, it's a boundary invariant. Okay, so in some vague sense that it detects the non-triviality in some sense of the boundary of these Lagrangians. So the relevant lemma that's very short is that if either K or L is compact, then the Rabinowitz wrapped Fukaya, the Rabinowitz wrapped Floer homology of KL is just simply 0. Okay. And that's because negatively wrapped Floer homology and positively wrapped Floer homology all are just ordinary Floer homology. Okay. Okay, so now I want to mention some basic properties of the category structure and some basic questions, and these are the questions that we're going to address in our work. So first of all, there exists an A-infinity functor, a canonical A-infinity functor. From the Rapp Fukaya category of X to this Rabinowitz Fukaya category. Okay. And this comes from the inclusion of subcomplex, you could think of. Right. So the Rabinowitz Rapp Fukaya category morphisms are cones, and this Rapp Floer homology is subcomplex. So this is A-infinity functor. The question we could ask is, can we ever compute the Rabinowitz category in terms, and this functor in terms of the ordinary Rapp Fukaya category? The second observation is, as we mentioned above, this lemma says that if K is compact, well, the image of K in the Rabinowitz category is a zero object. Okay, so this functor from the Rapp to the Rabinowitz category factors through a quotient by the compact Fukaya category. Okay, so the question is, so we know this map, this F is not an isomorphism because it already factors through a quotient, but is that all that happens? So the question is, after that, is F an isomorphism? Okay, so I want to point out already, just from definitions, that one sees that there's a potential mechanism by which this F bar could fail to be an isomorphism due to completion issues. Okay, by this I mean quotient categories are, that was supposed to be a laser pointer. These are, uncompleted objects. Okay, morphisms in the Rapp Fukaya category, direct sums. When you quotient, everything is a direct sum, so there's sort of no completed infinite rank things happening. Whereas in this Rabinowitz category, well, there's an inverse limit appearing. So it could result in something that's completed, and this could be a potential method by which F bar fails to be an isomorphism. Okay. So our first theorem addresses this. So maybe now let me state a theorem. Okay, so here it is. So the theorem with Gao and Venkatesh in preparation, and this answers the conjecture of Abu Zaid, is that, first of all, part one, there's a functor from the Rabinowitz Fukaya category of X to an object which I'll call W of X hat infinity. Okay, it's a category constructed purely algebraically from the Rapp Fukaya category. It's called the algebrizable categorical formal punctured neighborhood of infinity of the Rapp Fukaya category. It was constructed by Fmov. It's completely determined by the Fukaya category algebraically, okay, using some sort of non-commutative categorical construction. And this functor is compatible with natural functors from the Fukaya category to both of them. Okay, so the Fukaya category maps to both of them. And the second statement is actually this functor is an equivalence in nice cases when we have a Weinstein manifold or otherwise so-called non-degenerate manifold, meaning the open-closed map hits 1. So we know that Weinstein manifolds are non-degenerate by work of a number of people. I'm not going to focus on that, but the point is sort of whenever our symplectic manifold is sufficiently nice in the sense that, you know, it has a smooth Fukaya category, it has sufficient generators, the open-closed map's an isomorphism, then actually this map is an equivalence. Okay, so it follows that indeed the Fukaya category, the Rabinowitz category can be determined from this Fukaya category. So this okay, so what I want to do is I want to spend some time talking about this construction. Okay, so I want to focus on this construction, and then I want to say something about applications to mirror symmetry. If I have a couple of minutes, I'll say a word or two about the proof. So what's going on with this formal punctured neighborhood construction? So this was introduced in a recent paper of Fmov. And I want to tell you about the context in algebraic geometry first, and then we'll do something purely categorical. So in algebraic geometry, we start with an algebraic variety. Let's say it's smooth and non-compact. And let's fix a smooth proper compactification, which I'll call y bar, containing y. And let me call D the compactification divisor. Okay, and I the inclusion map from D to this compact y bar. Okay, so to construct this formal punctured neighborhood of infinity as a category in algebraic geometry, first we do something called formal completion. So we take the formal completion, this produces a formal scheme, which has a well-defined category of perfect complexes. And there's a natural map from perfect complexes on the compactification locus to perfect complexes on the formal completion, given by inclusion. Okay. So this category of perfect complexes is defined as some limit of categories associated to larger and larger formal thickenings of higher and higher order. And well, now what we want to do is we want to, so we now, you know, you could think of this as analogous to a tubular neighborhood. So now what we want to do is we want to consider the punctured tubular neighborhood. Okay. So the idea here is now to puncture by removing D. Of course, in algebraic geometry, it doesn't give you something well-defined as a formal scheme because the support of this formal scheme, y bar hat D, is just along D. It has no other points. So if you remove D, you removed everything. But so although this isn't well-defined as a formal scheme, the observation of Fmov is that you can still define a category. By quotient procedure. So you can define a category associated to this punctured neighborhood. Okay. Okay, just by simply taking the perfect complexes on the formal completion and then modding out by the essential image of perfect complexes on D. Okay. And moreover, this category, this only depends on the open locus. It doesn't depend on how you compactify. Okay. Which is also makes sense. And sort of you're really thinking of this as a neighborhood of infinity. You're compactifying, looking at a neighborhood, and then removing the compactification locus. So morally, it makes sense. There's a functor. This category comes with a restriction functor. Which is not essentially surjective. And let me just call the image, or the essential image, perf sub alg of y. Hat infinity, this is sort of algebraizable perfect complexes. Okay, just one orienting example. So if I start with A1, spec C join T, and restrict the structure sheaf to perfect complexes on the formal punctured neighborhood of A1, then the endomorphism ring I'll get is Laurent series in T inverse. Okay, so this is the construction algebraic geometry, and the observation of Fmov further is that this construction actually only depends on perf y. Okay, so in category theory, one can emulate this construction completely non-commutatively. What we want to do is we want to think of perfect complexes on the formal punctured neighborhood at infinity as some obstruction category to the variety y, hence the category of perfect complexes over y, being proper. Okay, let me just remind you that an A infinity or DG category is proper if the morphism spaces between any two objects are a perfect complex over the ground field instead of an arbitrary chain complex. So my notation is that perf K refers to those complexes with total cohomology finite rank, and mod K is all chain complexes. Okay, so we want to look at the obstruction to a category being proper, and now we want to study it in a purely non-commutative way. Okay.
Can I ask a question?
Sure.
In this example, the functor is essentially surjective, right?
No, it's
What?
I mean so the restriction to perf alg is essentially surjective. But you know there could be non-algebraizable.
Or C bracket T inverse?
Yeah, well, okay, actually, is it in this case? Maybe it is. I have that might be right, but I'm not sure. I sort of haven't thought so much about the non-algebraizable case.
I mean, it seems like since this is a field, every complex over this is quasi-isomorphic to its cohomology. So,
I didn't follow your comment actually. Can you repeat that?
The Lorentz series is a field, so every complex over that is quasi-isomorphic to it's cohomology.
Yes.
No differential.
I don't think it's a I don't think it's a cohomology versus chain complex issue. I think it's just sort of a, you know, you could have wild objects in the inverse limit of categories over formal thickenings that aren't restricted from an object on the total space.
Maybe I don't understand. What's the meaning of perf of C bracket T inverse then? Isn't it just complexes over
sorry. So this is not necessarily equal to, you know, so this is defined, you know, how do you define perf of y hat infinity? It's not by definition perf of C bracket T inverse. It's defined as perfect complexes on the formal completion and then you quotient, right? And perfect complex on the formal completion is some sort of limit of categories over thickenings. I don't know if that answers your question.
Yeah, I think it does. At least it's not obvious that it's essential.
Yeah, it's not obvious. That's right. So what's the obstruction to a category being proper? Well, there's a quotient sequence. Perf k sits inside mod k, and I can quotient by perf k inside mod k to get a category. Well, I'll just call it the DG quotient, mod k modulo perf k. This category is often called by Fmov calc k. This is the sort of category of algebraic Calkin complexes. So this Calkin terminology, as I understand it, comes from comparable construction in functional analysis. And so, well, we can study the obstruction to C being proper in terms of this localization sequence. So, of course, we observe tautologously that a chain complex is perfect if and only if its image in this Calkin category is 0. Okay, so how do we use this? Well, to construct an obstruction category for all of C. So for C, we'll look at, so what we're interested in is having the Hom pairing, which a priori takes a pair of objects and produces a chain complex. We're interested in it factoring through perfect chain complexes. And we can detect whether it factors by measuring how non-trivial its image of this pairing in Calkin complexes is. Okay, so we can look at the induced functor, which I'll call Hom bar, which is just J composed with Hom. Okay, so we can look at this, and the non-triviality of Hom bar as a bilinear functor, well, it measures failure of properness. And it can be detected. So we can measure the non-triviality of this pairing by another category. Okay, so we can detect the non-triviality of this pairing by looking at the essential image of the induced by this pairing functor from C to functors from C up to calc K, which sends an object K to Hom bar of blank K. Okay, Y for Yoneda, of course. So this is a Yoneda type functor, but I'm going to look at the Yoneda type functor as a as an element of the functor category to Calkin complexes instead of just chain complexes. Okay, so so the essential image of this, so if this essential image is 0, then Hom factors through perfect complexes by definition, and C is proper. If the essential image is non-zero or interesting, somehow C is not proper. So So indeed, we can actually just use this to be the definition. So here's the definition of the perfect complexes on the, the categorical formal punctured neighborhood of at infinity of C, at least the algebraizable version, is by definition the essential image of C under this map. Okay, so observations about this construction. So first of all, there exists a canonical functor again from the original category to this formal punctured neighborhood category. Secondly, it has an interesting property that reflects something we've seen in the Rabinowitz category already, which is that if I have a right proper object in C, meaning Hom into that object is always finite dimensional on cohomology, then its image, the image of this object under this Y functor is 0. So this canonical functor factors again through a quotient. Factors as a quotient, factors through the quotient of C by such proper objects. Another observation is actually the formal punctured neighborhood at infinity is not generally a functorial construction. Okay, so as up to Morita equivalence, it only depends on C up to equivalence, but it's not functorial in C. Okay, the same way that a map between algebraic varieties doesn't always induce a map between their neighborhoods of infinity if the map is not a proper map. Okay, so similarly, you need some sort of condition on functors. So it will be functorial under so-called proper maps, which are those with left adjoints. Okay, so let's see. I want to state one theorem of Fmov, and then I want to talk about some applications to mirror symmetry. So Fmov proves some very nice properties about this construction. So first of all, yes, go ahead, question?
I would think of the, so it wouldn't be complete analog of proper, but I would think of a categorical version of the proper map as something like C2 is a perfect bimodule over C1 or something like that. Would that also imply that it is functorial? Is
I mean, certainly, okay, I have to think about it a little bit, but certainly there is some condition involving perfection, which you can think about as an analog of proper, and one way it might correspond to a bimodule being perfect over the other. I mean, just which direction I won't be able to produce on the spot. Yeah, no, but thanks, absolutely. I mean, there's definitely a version of this. Okay, so here's some theorems so that tell us it recovers known constructions in algebraic geometry. So first, if Y is smooth and non-proper, this is the case we talked about earlier, then this categorical construction recovers the algebra geometric construction. Okay, so if I take perfect complexes on Y, take this purely non-commutative construction, I get perfect complexes on the formal punctured neighborhood at infinity. There's another case where it recovers a category of interest. So if I have a proper singular variety, okay, so compact variety, possibly singular, then the same construction So what's happening in this case? Well, in this case, we have perfect complexes on Y sitting inside coherent complexes on Y, and they're not necessarily the same. And in fact, perfect complexes on Y is proper, and it's sitting inside coherent complexes on Y, a smooth category. Not necessarily proper. And we can ask what happens when I take the categorical formal punctured neighborhood at infinity of coherent complexes on Y. That's the one I'm interested in. And it won't be interesting if I apply it to perf of Y, because perf of Y is a proper category, and this construction vanishes on proper categories. So that's the reason we use co. And in this case, I actually get the singularity category. Okay, up to some maybe up to some variance issues. So I won't get into that. Okay, so this is by definition co mod perf. So more generally, there's a more general statement that implies this second statement, which is purely categorical. So let's say C. I'm going to identify C with its split closed pre-triangulated hull. Let's say C is smooth and has a causal dual subcategory, proper subcategory. D sitting inside it. Okay, and to be causal dual, this means that D, even though it seems smaller, it's a proper subcategory. It actually knows all of C. Okay, so C can be recovered as finite, functors which take values in perfect chain complexes. So this is sort of, you might think of it as the categorical dual of D. So this situation occurs a lot, and when you have a situation like this, then first of all, you could look at C mod D, which again, I've identified everything with their pre-triangulated split closed hulls. So I can think of this as perfect modules over C modulo proper modules over C. This canonically maps, by what we've said earlier, to the categorical formal punctured neighborhood at C. And the statement is that then this map is an isomorphism. Okay, so in the situations of causal duality, there's no completion happening, and this sort of abstract singularity category associated to the smooth category is isomorphic to the categorical formal punctured neighborhood. Okay, and there's an analogous construction of abstract singularity categories in this context by Rivera and Wang. So they consider something for proper categories instead of smooth categories. So there's a way to start with proper category instead. And so 3 implies 2 because essentially in this setting, when I'm in the setting of 2, co and perf have this relationship to each other. So I sort of won't spell that out since I'm very short on time. So I'm just going to take a minute and state some applications. So from our main theorem and Fmovs, we get some corollaries. Okay, so so first of all, let's say I have a homological mirror symmetry equivalence between the Fukaya category and a coherent complex category. Then actually the Rabinowitz Fukaya category also fits into mirror symmetry as the categorical formal punctured neighborhood of infinity of the coherent complex category, which in the cases considered by Fmov, we can identify with something geometric. We can identify with either the algebraizable perfect complexes near infinity if Y is smooth and non-proper, or with the singularity category up to, maybe some variance issue in the proper non-smooth case. And there are examples in which this is the form of mirror symmetry that takes place. For instance, T star S1 has, oops, there's a missing star. It's mirror C star, smooth non-proper, and T2 minus a point has mirror a nodal elliptic curve. And okay, maybe I'll just say one other thing. When the RAP Fukaya category has a causal dual subcategory, and Yin Li yesterday talked about many situations in which this arises, then the Rabinowitz category is just the quotient by compact Lagrangians. If it's possible, I'd take one more minute and say one thing about the wrapped Fukaya category, about this comparison. So how to prove the theorem? Okay, so the first, maybe I just want to make one comment, which is that we have two different categories. We have, on one hand, this Rabinowitz category, which at least as a complex, its morphism spaces, maybe I'll say it this way. Look like the cone of some map from negatively wrapped Floer homology to positively wrapped Floer homology. Okay, and negatively wrapped Floer homology is determined by positively wrapped Floer homology by this Punctured duality. So so it might seem that it's determined by W, but there's this map C, which is actually not determined by W. So this Rabinowitz category would seem to not be determined by W, whereas the formal punctured neighborhood at infinity is determined by W. So actually, our isomorphism needs to use some extra information. So the point is somehow C can be determined via the Calabi-Yau structure on the RAP Fukaya category of a Liouville manifold, which is non-degenerate. Okay, so there's this Calabi-Yau structure that formally allows one to determine this map C. So our map also makes use of that Calabi-Yau structure. Okay, well, let me stop there. Thanks very much.
Thank you, Sheel. Questions, comments?
Hi, Sheel. I have a question. Great talk. I really enjoyed it. So if you scroll up a little bit in this last application you had, so about this cases where you have this causal dual subcategory.
Yes.
Do you think you can get some kind of answer to the question above by putting stops on X?
Question about.
Yeah. Let me think about that. So I mean, the thing is, okay, so you mean this question here. So there's this question, there are of course cases where we have non-smoother proper mirrors. So for instance, the case of, xy equals 0 is mirror to the, so on the B side is mirror to the pair of pants on the A side, with a certain, holomorphic volume form. I've written some degrees. Okay, and the idea is what's happening with this categorical formal punctured neighborhood is, well, we can still take this and it's still going to be isomorphic. So the Rabinowitz RAP Fukaya category of X is going to be isomorphic. It will always be isomorphic to the algebraic categorical formal punctured neighborhood of coherent complexes. But the question is, in algebraic geometry, what is the meaning of that? So it's something that's sensitive to both non-compactness and singularities simultaneously. So you might think of it as it views singularities as a form of non-compactness in some sense, some very vague sense. So yeah, maybe my question was, this question, which I didn't have time to really talk about, was more of a purely algebrogeometric question, which is...
I see, yeah. And then I have another question about the stuff at the end.
Sure.
About the Calabi-Yau structure. So you said you can get the RW from taking the cone of this mapper?
Yeah, at least on morphisms. At the
Morphism.
level of different morphisms, that's right. So the algebra structure is something additional, but...
Do you get something that should be like analog of cohomology or compactly supported cohomology of your manifold in string topology?
Sorry, so can you ask that question again? So in string topology, you have the free loop space. Go ahead.
No, if I remember right, in the string topology case, define it as cone of factoring through compactly supported then supported cohomology.
Yes.
Right. Is that what this thing in the middle is supposed to be?
Yeah. So C, right, indeed. So C is like, okay, so you could think of it as we have this map from negatively wrapped Floer homology to compactly supported cohomology of L to cohomology of L to ordinary wrapped Floer cohomology, and C is the composition.
Mm-hmm.
But categorically, I want to note that we don't recover these pieces from the Fukaya category. We just recover the map C.
I see. Okay.
So for instance, there are cases in which wrapped Floer homology is completely zero. So there's no hope of recovering the cohomology of L just from the Fukaya category or the Fukaya category and its Calabi-Yau structure. But you can recover this composition.
I see. So there's no sort of analog you get from this. I see. Thank you.
Mm-hmm.
Any more questions? Well, thank you, Sheel. Thanks for the great talk. And thank you, everybody, for listening. And that's it for this meeting. I'm going to shut down the recording.